In this lecture, we're going to begin the second part of this course on calculus. We already have a good understanding of differential calculus, and we're going to begin integral calculus. Now, integration is going to be defined as the very opposite, the inverse of integration. Let me explain what I mean. Now, this might sound a little abstract, but it's actually going to be quite easy. I'm going to define the operation of integration as being the exact opposite or the inverse of differentiation. You've understood the operation of differentiation very well, of course. So suppose I have a function f that depends upon x. I take the values of the function at two slightly differing points and I divide by the difference of the arguments between them. And as h becomes smaller and smaller, this becomes the derivative at the point x. Now, I'm going to introduce a brand new symbol. It's like a long s, and the function f of x is integrated by this symbol over here. At the very top, I'm going to put the variable or the number s, and this is going to be called the integral of the function f for the value s, and this s occurs at the upper point over here. It does not matter at all whether I had called this x or y or z or t. So to be definite, let me call this f of t dt, and as long as the same s is over there up above, this too will be the same thing, I of s. In fact, mathematicians these days, they don't even bother to write x or t or whatever. This is good enough. But we shall usually write x or t or some other thing over there to make things a bit clearer. Now, let's draw a little picture of what goes on. So, we have a number s that's fed into this integrating machine or integrator, which gives out a number I that depends upon s. So I stands for integral, as I said earlier. But this machine has got to have some constraints. It's got to fulfill some requirements. Here is what the requirement is. I of s has to be such that when differentiated, it gives you f. So, if I take I, differentiate it, then the I prime that comes out, the derivative that comes out, has to be f. That is why, in this way of defining the integral of f is the antiderivative of f. Now, what that means is the following. Let's do a couple of examples. Suppose I look at this, dx x squared. Well, I say this is integrated up till s, and so the result of this I say is s cubed divided by 3. Why? Because when I differentiate s cubed over 3 with respect to s, then I get s squared. And that's what the function is over here evaluated at s. Or let's take another example. Let's take dt, t to the, let's say, 7. Well, the value of this is then s to the power 8 divided by 8. Why? Well, that's because if I differentiate s to the 8 over 8, then you know by the rules of differentiation we discussed that this is just s to the power 7. Let's do some practice integrations, beginning with the first integration over here. Now the answer that we have comes about because I know that when I differentiate x to the n plus 1 divided by n plus 1, then the answer is exactly x to the power n by the rules that we had discussed. So simply differentiating what's over here on the right hand side, if we get what's inside the integral, and this is by the way also called the integrand, then we know that we have succeeded in doing the integral. Of course, this particular formula holds except for n equals minus 1. We'll see later what happens in that case. Similarly over here, if I differentiate sine of x, well, I get cosine of x. But cosine of x is exactly what's over here. Or if I differentiate cosine of x, then I get minus sine x. And of course, differentiating minus cos x gives you sine x. This is even easier. We know that the exponential is defined so that when you differentiate it, you get back the same thing. And so the integral of e to the x is e to the x itself. This is only a little bit harder, but we've done that earlier as well when we were talking about inverse functions. And you remember that if you differentiate tan inverse, you get 1 over 1 plus x squared. And similarly, if you differentiate sine inverse of x, then you get 1 over square root of 1 minus x squared. Now, here is something that requires the chain rule. If I have a function raised to the power n plus 1 and I differentiate that, well, then immediately I get n plus 1 times f to the n, and then I have to differentiate by the chain rule the function f itself, and so that's f prime. The point is that this, when differentiated, gives you what's inside over here. And so this is absolutely the best way by which you can do an integration. If you know the derivatives of functions, you remember lots of them, then you'll be able to do lots of integrals yourself without any problem. You're now going to hear a new word, indefinite integral. Here's what the integral is of the function f with the number x up over here, and that is why this capital F is a function of x. Whatever you put in over here comes here. Now, we call this the indefinite integral, and the question is why? Well, let's remember that if you take f prime, then you must get back f itself. But what if you had put, instead of what's up over here, f plus, let's say, the number 5, and taken its derivative? Well, of course, you would get back f prime itself, and that's equal to f. So, the point is that f plus 5 works just as well as f. In other words, if instead of f of x, I put f of x plus a constant c, that's just as good as the original f itself. And this c over here can be arbitrary, which means anything. And so we don't have the integral as being definite. There's some ambiguity, there's some arbitrariness. And now let's see what this then points towards. This points towards the definite integral, which I'm going to define in terms of the indefinite integrals that we encountered earlier. Now, f of b is just the integral of small f up till b, and f of a is the integral of f until a. their difference is called very commonly integral a to b. So a is called the lower limit and b is called the upper limit. And now, of course, it doesn't matter whether it is x or t or whatever. The limit a to b f of t dt is exactly the same as this, and mathematicians generally like to simply write a to b f. No x, no t, all of these mean exactly the same thing. And I'm going to call the difference between f of b and f of a g of ab. Now, this is the definite integral. Why is that? Well, this is because of the first of four properties that I'm just going to discuss. You remember that in f of b, you can add any constant number c. Well, you must add that same constant number to f of a as well. And now this constant c cancels out. It doesn't matter what value you took for c, it simply went away. And so this is g of ab, or you could write this as integral dx f of x from a to b. And now this is perfectly definite in the sense that the value of c, the arbitrary constant, is irrelevant. There's another obvious property. Let's say that I go from some number to the same number. Well, that's just f of a minus f of a, and that's 0. Or another way of writing this is that integral a to a dx f of x is 0. So the integral where the limits are the same, it has to be equal to 0. Another property, obvious of course, that gab, which is f of b minus f of a, is minus gba. In other words, if you reverse the limits of integration, the sign of the integral changes. Or you could write it in this way: ab is minus ba. And of course, I could have omitted the x's and just put t or something else. A very important property is the following. Suppose I take gab, add to this gbc. Well, if I look above at the definition, this is f of b minus f of a, that's gab, and then I add to this f of c minus f of b, and that is gbc. But f of b cancels out, and so this is just f of c minus f of a, which is equal to g of ac. So you can go from a to b, b to c, and it's the same as going from a to c directly. Now, you can write this as integral a to b f plus integral b to c f as directly equal to a to c f. And now you can extend this to any number of points in between. So let's say that you went from a to b1, and then you went from b1 to b2, and then you went from, let's say, all the way from b100 to c. Well, that's still the same as going from a to c. So you can break up your journey from a to c into 100 different parts, or maybe even 1,000,000 different parts. It's the same thing. Let's quickly recall what we've learned about the definite integral. This definite integral of the function f of x goes from a to b. This is the lower limit, this is the upper limit. And this definite integral is equal to the difference between the function capital F evaluated at the point B minus capital F evaluated at the point A. The only thing that we know about capital F is that its derivative at any point x between a and b has to equal the function f itself. Or if you insist upon writing x, well, let's write it this way. But as yet, it's very abstract. We need to understand this better, so let's make some pictures. Here is the point A, the point B. Here's the function f of x, and x is a number that's increasing in this direction. Now let's put a third point over here, which is at a distance h from it. So if this is b plus h. And we have just learned that if you go from a to b, and then from b to c, well, c over here is b plus h, that's the same as going from a to c itself. Now, that is something that we're going to use very soon. But let's first look at this definition over here and ask what it means when we apply it to the point B. Well, f prime at B is defined to be f at b plus h minus f at b divided by h. And this is going to be true as long as h becomes smaller and smaller, as small as we like. But now let's put in what this is. This is 1 over h, and we have integral a to b plus h, f of x dx, minus a to b. So the upper limit here is different. It's b instead of b plus h. Okay, now I can now switch this a and put it up over here and take b down, but then I will have to change the sign over here. And so this is equal to 1 over h. And now I'm going to have a to b plus h, f of x dx. But now I have a plus b to a, f of x dx. Now, I'm going from b to a, and then from a to b plus h. So from what we've learned over here, this is exactly equal to 1 over h integral. Now, we're going from b to b plus h, f of x dx. What this tells us is something very interesting, that the integral of b to b plus h of f of x dx is equal to h times f prime of b. But what's f prime of b? According to what we have over here, what we started with, f prime of b is equal to f of b itself. So it's h times f of b. So now let's come to this diagram over here. H is this distance, and f of b is this height. So what is h times f of b? Well, that's pretty close to this area that is between b and b plus h. And if h becomes smaller and smaller, you can see that the integral from b to b plus h is just going to be this area. And so now we have an interpretation of the integral which we had defined only in very formal terms over here. Now you could say that this is just a tiny little area over here, but let's remember one thing. We could have broken up the distance between A and B, or B plus H, into 1,000,000 different pieces, or even 1,000,000,000 different pieces, or we could just have kept dividing and then subdividing. And so what we are coming to now is that this definite integral from a to b of f of x is actually going to be the sum of the little areas that are under the curve f of x. Here's a quick summary before we move on to solving some examples. We have supposed that f is a continuous function in some interval, that if a and b lie within this interval, then this integral of f from a to b, the definite integral, is the area, or rather it can be interpreted as the area under the curve from a to b. And crucial in this is that the integral from a to b can be split up from a to b1, b1 to b2, b2 to b3, and so forth until you get to b100 to b, or maybe b1000 or b,000,000 or b,000,000,000. So the point is that between a and b, we can keep splitting up the interval into finer and finer pieces, and each one of these, as we showed earlier, is the area under this curve over here. Now, crucial to all this is that f here is continuous, and that if you take the indefinite integral f, that is capital F, and the property that defines it all is that f prime is equal to f, and this is true at every point x. So f prime of x is f of x for any x that lies between a and b. Let's quickly work out a few examples. We want the area between x equals 1 and x equals 3 for the function f of x equals x squared. Now, of course, if you were to plot the function f of x equals x squared, that's what it looks like. It goes up like that. So we want the area, let's say, between x equals 1 over here and x equals 3 here. So this is the area that we want. Written in terms of formulae, this is the integral of x from 1 to 3 of x squared. And now you know that when you integrate x squared, you get x cubed over 3. Now this has to be found at the value x equals 3, and then at x equals 1, and we subtract the 2. The way this is normally written is you write 3 on top, 1 at the bottom, and then this is 3 to the power 3 over 3 minus 1 to the power 3 over 3, and that's 27 minus 1, which is 26, divided by 3. That was simple enough. Let's take another example. We want the area between x equals 0 and x equals pi for this function. F of x is sine x. And of course, the way that you would first think about this is, here's sine of x, it goes up and it comes down. When x is equal to pi, it's 0 again. Now, what we want is the integral dx from 0 to pi of sine x. You know, of course, that if you differentiate cosine x, you get minus sine x. So minus cosine x when differentiated gives you sine x. And now this must be evaluated at pi and the value 0 as well. And then we must subtract this. So this is minus cosine of pi plus cosine of 0. And that cosine of pi, you know, is minus 1. So the answer here is 2. So that's the area that we've just calculated. Its value is 2. Now, areas can be both positive and negative. So, if we take between here and here, where the function is positive, then this area here is positive. On the other hand, here the function is negative, and so if you were to do the integral from, let's say, 0 to b, then you would write it as two parts, 0 to a and then a to b. But the integral from 0 to a will be negative, and the integral from a to b will be positive, and to an extent they will cancel. If you were to do an integral like this, dx, let's say sine of x from 0 to 2 pi, well, even without doing the integral, you know that the area will be 0 because sine goes up and comes down. So whatever area you have between 0 and pi, between pi and 2 pi, you're going to have something that's equal but with a negative sign. And if you want to check this, then let's take our earlier answer, minus cosine of x, evaluated between 0 and 2 pi. Well, this is minus cosine of 2 pi plus cosine of 0. And now cosine of 2 pi is 1. And so we have minus 1 plus 1, which is 0. So this area here has cancelled exactly with this area here. For the very simple functions that we've looked at so far, the indefinite and definite integrals have both been very easy to do. But now I'm going to take an example, f of x equals 1 over x, where doing the indefinite integral is very easy, but you've got to be careful about how you do the definite integral. Well, integral dx over x is just log of x, or if you like, you can add some constant to it. After all, this is an indefinite integral. Why is the answer log x? That's because log of x when differentiated gives 1 over x. And if you don't remember this, go back to the previous modules. Now let's say that I want to do the integral from 1 to 3 of this function. By the rules that we've discussed again and again, this is log of 3 minus log of 1. And that's log of 3 over 1. There's no problem on that. Of course, I could have just set log of 1 equal to 0, but then you see that it's the same thing, log of 3 and log of 3 over here. So there is no problem here, but just to be sure as to what we are doing, let's sketch. So here is our function which is going to 0. We've taken x equals 1 and x equals 3, and we're looking at the area under this, and so that's this area. And we found it to be log of 3, which is something that you can look up in the tables for. Well, what if it was minus 1, or rather minus 3 to minus 1? In that case, we would have log of minus 1 minus log of minus 3, and you could then write this as minus log of minus 3 over minus 1, which is minus log of 3. Now that also makes a lot of sense, because let's plot log of x for negative values. And so let's say that this is minus 1 and this is minus 3. Then we're looking at the area over here between minus 1 and minus 3. And this is just as much area as over here, but it's down here, it's negative, and so we get minus log 3 as the answer. But now what if I ask what is 0 to 3 dx 1 over x. Now this gives me log of 3 minus log of 0, and you can see that because log of 0 is not defined, it's infinite, in fact, negatively infinite, that this is not in number. And so we say that this integral over here does not exist. And similarly, if I had asked what is 0 to minus 3 or minus 3 to 0, that would not exist either. What about minus 1 to plus 1? Now, here again, we have a function that whose indefinite integral is log of x, but here I would have log of 1 divided by minus 1, and this would be completely the wrong answer. In fact, this function over here cannot be integrated because it is not continuous in the range of integration. You see, the problem is over here at the origin, where the function blows up as you go to smaller x from the right side and blows up as you go to larger x from the negative side. So in general, you cannot say that the integral of 1 over x will exist. It all depends upon the region of integration. In other words, the lower limit and the upper limit. We began with the notion that integration is the opposite of differentiation. And following this line of logic, we saw that it also has something to do with area. In the next lecture, we shall see its relation to the summation of an infinite number of terms, and that will be another view of integration.